Hi. In the previous segment, we discussed ordered pairs and Cartesian products. Using these ideas, we'll now turn to our main topic of relations. The basic definition of a relation is very simple. A binary relation from a set A to a set B is simply a subset of the Cartesian product A cross B of the two sets. In other words, a binary relation is nothing but a set of pairs where the first component comes from the set the relation is from, and the second from the set the relation is to. Often, a relation relates elements of the same set to one another, so the two sets connected by such a relation are really the same set A, and the relation is a subset of A cross A, or A square. In that case, we also say that it is a relation over A. Like Cartesian products, this generalizes easily to relations involving more than two things from more than two sets. An n-place relation is simply a subset of a Cartesian product of n sets. That is, it is a set of n tuples. Relations are extremely common in all branches of math, and often a more economical notation is used by writing the name of the relation or a suitable symbol representing it between the two things related by it to indicate that the pair of these two things actually is contained in the relation. So instead of writing the pair AB is an element of R, we can also write ARB to mean exactly the same thing. Let's look at an example. Suppose C is the set of a number of European countries. Then we could represent the existence of a land border between two nations as a relation, here represented by the bow tie symbol as follows. Then, to indicate that, for example, France shares a land border with Switzerland, we write F bow tie CH, and to signify that Spain and Italy do not, we write E not bow tie I. The bar through the relation symbol denoting that the given pair is not in the relation. Here are a couple of examples. First, let us define the less than relation on the positive natural numbers. The relation relates natural numbers to other natural numbers, so it is a subset of the Cartesian product of n plus with itself. Then, we can define it to be all pairs AB of positive natural numbers for which there is another positive natural number C, such that A plus C is B. The result of this would be a set of pairs like this one. Here the pair 4, 7 is an element, but 2, 2 and 7, 1 are not. Now suppose we define a family of sets like this, similar to the one we defined before. Each mi contains all the multiples of I, this time though including I itself. Now let us use these mi to define a relation R over the positive natural numbers like this. What does this relation represent? When is ARB? That is, when are two values A and B related to each other by it? The answer is when A divides B. Now we'll look at some terminology pertaining to relations. First, for any relation from a set A to a set B, we call A its source and B its target. It's important to know that in general, one cannot tell source and target just from the set of pairs representing the relation, at least not uniquely. Because any relation from A to B is also a relation from any larger set than A, say A prime, to any larger set than B, B prime. The following two things, however, are direct properties of the set of pairs. The domain of a relation is the set of all values that occur as first component of at least one of the pairs in the relation. We also say it is the set of all left-hand values of the relation. Correspondingly, the range of a relation is the set of all right-hand values. That is the set of all values that occur as the second component of at least one pair in the relation. Therefore, it is always the case that the source of a relation must include its domain, and its target must include its range. As an example, let's look again at a network of romantic interests among some of the Peanuts characters. Let's say we have two sets of these characters, P and Q, and a number of documented crushes, the R's. We can represent the same information as the relation from P to Q like this. Note that Sally does in fact have a crush on Linus, since the pair Sally-Linus is an element of the heart relation, but Sally does not have a crush on Schroeder, because the pair Sally-Schroeder is not. Now let us look at different ways of representing this relation apart from listing the pairs in it. Here we represent the same information as before using a table. The elements of P are labeling the rows of the table. Those of Q are labeling the columns. Each cell contains either a 1 when the corresponding pair of labels is an element of the relation, or a 0 if it isn't. Another way of drawing relations is as digraphs, or simply graphs. To draw a relation from P to Q as a digraph, we draw the elements of P in a bubble, then those of Q in another bubble, and then we draw an arrow from an element to P to one in Q if the pair of the two is contained in the relation. This means that we end up with as many arrows as we have tuples that are elements of the relation. Suppose we change the source of the heart relation a little by making it Q instead of P. Q is a proper superset of P, so we effectively add a few more missing elements to the source. We can then simplify the digraph representation by using the same bubble and the same elements in it as both the origin and the destination of the arrows representing the pairs, like this. Notice how, for example, self-love, a direct circle, the one that Violet is involved in, and reciprocity, such as, for example, the one between Sally and Linus, are directly visible in this representation, as is the formation of cliques, that is, groups of people that are connected amongst themselves but separate from others, such as the cliques around Charlie and Linus and the one involving Lucy and Schroeder.